Alright, hi Year 12s, this is Mr. Lim here again, and this is our first video in the Year 12 Acids and Bases series about the theories of acids and bases. Right, continuing on from what we learned last year. Okay, so here's what we're going to be learning. Let's get started. Okay, so we learned about Arrhenius last year, and we're going to learn about two more. This is the first one, Davy. So Davy thought that acids were substances that contain a hydrogen that could be totally or partially replaced by metals. Okay, so the idea is that, okay, I have an acid like HCl, hydrochloric acid, and if I put a metal in it, right, the metal will replace the hydrogen inside that compound, and then it will also form H2. All right, so just the idea that this particular metal replaced the hydrogen to form magnesium chloride, or the metal chloride in this case, and that was the theory. Okay, so based on the reactions of acids with metals, okay, as I said last year, this is a redox reaction, and we will be covering it again in the redox topic. And remember that the only acids to react are the reactive metals, which have a negative value on the standard reduction potential table on the back of the data sheet. Okay, so not all metals will undergo this reaction. You have to go to the back of the data sheet, check where that metal is, and if it's below 0 or it's a negative value, it will undergo that reaction. If it is above it, then it will not. Okay, so that was Davy, nice and quick. Let's move on to Bronsted-Lowry. Okay, so Bronsted-Lowry says that all acids are proton donators and all bases are proton acceptors. Okay, so this was the next logical step from the Arrhenius theory. Okay, because the Arrhenius theory had various limitations, and if we remember the limitations is that they were only dealing with acids and bases in solutions, so this process allows reactions to be conducted outside of water, because you can have proton transfer outside of aqueous solution. Allows for substances without OH to be classified as bases. Okay, so in Arrhenius theory, you had to have the OH, and then it would have to form OH minus in solution. But now you can have substances that don't originally have OH to be classified as bases, because they can still just accept a proton. And then also allows the creation of the hydronium ions, because remember, the hydrogen ions were not stable in solution, and so therefore if that hydrogen was or went to or was donated to a water molecule, it would form a hydronium ion, and that is much more stable, right, than the hydrogen ions in water. So this Bronsted-Lowry theory just effectively builds on the Arrhenius theory and deals with some of its limitations. Okay. It's not actually the last acids-based theory. You'll learn about Lewis theory if you go into university about it, but we're just going to stop at Bronsted-Lowry. Okay, so let's have a look at some of the ideas. Okay, so let's go write out some Bronsted-Lowry theory stuff. Okay, so hydrochloric acid in water. So the idea is that the hydrogen chloride, right, when you add it to water, okay, this is how you make hydrochloric acid, right, you will make H3O plus and Cl minus. Okay, the idea is that this proton here has been transferred to this substance here, and what you've ended up with is H3O plus. There has been a proton transfer where this has donated and this has accepted a proton. Right, so the proton has been donated and then accepted by the two substances there. All right, that makes this the acid because it is the donator, and this the base because it is the acceptor. Okay, let's have a look at different things. All right, what about hydrochloric acid? Okay, so you should remember that hydrochloric acid as a solution is the Cl minus is not going to do anything. The H3O plus is going to be the thing that does the action, right? And so when I put that with some sodium hydroxide solid, all right, it's going to form, okay, so this is going to transfer a proton, one of those protons, to this substance here, all right, and then it's going to form H2O and Na plus, and there's going to actually be two H2Os because there's going to be the H2O that's left over after this thing has donated a proton. Okay, So the idea is that now, before when we did Arrhenius, we would just show a H plus here, right? But now we're showing the H3O plus because that's the thing that actually exists in the solution. This donates a proton to this over here, which has accepted the proton. When it accepts a proton, it forms a water. When this one donates a proton, it forms a water. So that's where the two waters come from. And this falls apart and forms a positive ion, which will be in solution. Okay, so that's a liquid and that's aqueous here. Again, this is the donator and this is the acceptor. That makes this the acid and this the base. Okay, and let's have a look at ethanoic acid. Now, ethanoic acid, if you remember, is a weak acid. So we write that all together. Okay, with a solution of potassium carbonate. So it's because it's a solution, we can split that apart. Okay, so potassium carbonate. Now, hopefully you remember that with a weak acid, you need to put double arrows in. Okay, and then an acid plus a carbonate makes carbon dioxide, gas, and water, liquid, and the salt, which will be potassium ethanoate, which is the negative part of that acid. Remember that ethanoic acid is a monoprotic acid, so it'll form this. You would check if this precipitates, which it does not, right? And so therefore, because this does not precipitate, right, you don't write it together, you get rid of your spectator ions, which is this and this, okay? And that would be your reaction. To balance this reaction, you'd need a 2 here, so you'd need a 2 there as well to make that balanced. Okay, so let's look at what's been accepting and donating. So this is donating. Okay, what is it donated? It's donated this proton. Where is it donated to? It is donated to this substance here, where the oxygen has fallen off to form water and carbon dioxide. So this substance here has accepted, whoops, that's not what I wanted, accepted a proton. Okay, so therefore this is the acid and this is the base. Okay, right, and that's how you would write out those, but that's the idea about working out which one's the acid, which one's the base from donation and accepted. Okay, let's move on. Right, when acids are in solution, they hydrolyze as water. They can show this by a hydrolysis reaction. Okay, so this is what we were saying before. Nitric acid, which is the molecule, in some water will form, single arrow because it's a strong acid, okay, H3O plus AQ and NO3 minus AQ. So in nitric acid, it's really the H3O plus that will do all the reacting with stuff because all of it has ionized. It is completely ionized because it's a strong acid. However, ethanoic acid, AQ plus some water. Remember that this is a weak acid, so we do a double arrow, okay? Only some of it will turn into H3O plus and CH3COO minus, which means that we have to show this as a CH3COOH, all right? But the idea is that this is still, oops, not that one. This is still being donated to this, which makes that this is the acid and this is the base, okay? Right, so those are the ideas about identifying acids and bases. Let's move on. Okay, conjugate acid and base pairs. So let's have a look. When an acid donates a proton and a base accepts the protons, they're called the acid and the base. So we dealt with that already. The substances that are produced are called the conjugate acid and the conjugate base. Okay, so let's have a look at what these reactions that we've done. Let's go grab a few. Let's grab this one. Let's move that one down here. Nope, that's not what I wanted. And let's move a few more. Let's take this here as well. that's not what I wanted. Here we go. Oh, come on. Come here. There we go. All right. So we should be able to identify whatever conjugate pairs in these two particular reactions. Okay. So here we have the substance that is donating a proton. That's the donating of a proton. Okay. So what's left over once it's donated a proton? It's this one here. Okay. So then this has accepted a proton, and what's left when it has accepted a proton? This one here. Okay, so the idea is that this is the acid, this is the base, and then this and this is its conjugate base. Okay, and this is over here. Oops. Over here is its conjugate acid, okay? Because it is the pair, or what is produced from that particular transfer of a proton, okay? So this becomes one pair, and these other two become another pair. This one here and this one here become a pair, right? So those are the two pairs, right? They differ by one proton each. Okay, so if you look at this one here and this one here, there's a difference of one proton. If you look at this one here compared to that one here, there's a difference of one proton. Let's have a look at the next one here. Okay, what is the conjugate acid and the conjugate base? Okay, so this one here, right, after you leave one of those, it is this one here, right? So it is donated a proton, it forms one of those, all right? The base is the OH minus, or the NaOH. When it receives a proton, it is also this one here, okay? So the conjugate acid is this, the acid is the H3O plus. The conjugate base of that is H2O, all right? So maybe it might be better to show it as one of the H2Os here, one of the H2Os here. So this acid here has donated a proton. What's left over? A H2O, right? This OH minus has accepted a proton from over here. What's left over? Once it's done so, another H2O, right? So this is one pair, and that's one pair. Okay, they differ by one proton each, a H3O plus and a H2O, and an OH minus and a H2O. Okay, so this here is the acid, and this is here is the conjugate base. This is the base, and this is the conjugate acid. And you notice that the conjugate acid and the conjugate base are exactly the same thing, and that's fine, all right? All right? Doesn't have to be something different, all right? But you've got to recognize they differ by one proton, and they're what's produced, right, after the transfer of the proton has occurred. Okay, then let's have a look at the next bit. Okay, so conjugate pairs differ by one proton or hydrogen, so the conjugate acid or base of a substance can be identified. So you pick some random stuff, right? Conjugate acid has one more proton, and conjugate base has one less proton. So let's have a look at the hydrogen phosphate ion. Okay, if I want to find the conjugate acid of this, it's going to have one more proton. So that's going to be H2PO4 1-. That's the conjugate acid. What's the conjugate base of this? It's going to be PO4 3-. Now, what I want to make very clear is that these two are not conjugate acid-base pairs. This is a pair, and this is a pair, right? So this is the conjugate base of this. This is the conjugate acid of this, right? So this has the ability to accept and donate a proton, and we'll deal with that in a later video. But the idea is that this is one pair, this is one pair, right? You can do the same thing with water. Okay, let's move down a bit. Same thing with water, H2O. Okay, what is its conjugate acid? Okay, it's going to have one more proton, so it's going to be H3O plus, right? What is its conjugate base is going to have one less proton. One less proton than what? One less proton than the water. So it's going to have OH minus. So this is one pair, and this is one pair. And this is exactly the same idea that we had with that last equation, right, where the H3O and the OH minus combine, and then that H2O is the conjugate acid and the conjugate base of those two things, right? So that's the ideas between the Bronsted-Lowry theory. We'll move on to the next one. Adios.